So we just saw some beautiful examples of self-organized collective behavior in very different aquatic systems in Mexico, whether it's the open ocean or the stinky sulfuric springs that David showed. So, but what is self-organization? Actually, it's a phenomenon we see everywhere in nature. It's whenever we have multiple components, many components that interact together and we bring them together, at some point we see emergence of structures, dynamics, patterns at the macroscopic, at the collective level that cannot be really predicted or are very hard to predict from the properties of individual components. And the prime examples of this nature are snowflakes. You've all seen them and they assume all beautiful shapes. However, there's nothing in the properties of water molecules and their interaction that actually determines the shapes and the diversity of these beautiful patterns. They actually emerge through a process of self-organization through the interaction of very large number of these molecules together with the environment and under different environmental conditions like different temperatures and different humidities. And while beautiful, the snowflakes are certainly not intelligent. And what is fascinating, however, now about self-organized animal systems is that they actually evolved to be in this collective state. They evolved to harvest the power of self-organization to behave collectively in an intelligent way because it gives advantages to the individuals in such a collective, animal collective. So self-organization as a phenomenon actually constrains and determines what collective behaviors can such a system do. On the other hand, however, the adaptive behavior of individuals will also affect the self-organized structures that emerge in such a system. So we have a complex loop between these two different aspects, which is actually what is the foundation of the emergent collective intelligence that we see so beautifully in these different examples in nature. And what makes this system really truly fascinating, but also complex to study. And this loop is also one reason why it's intrinsically hard to actually engineer artificial collectively intelligent systems. Because how would an engineer do this usually? He or she would just start with designing a single robot. So how does it move? What sensors does it have? How does it interact with other robots in its vicinity? And all this with having in mind a certain function or task to be solved by the robot collective. However, once you put or you generate such a large group, you put many robots together, because of self-organized phenomena, new effects will emerge on a collective state, on a collective level, that actually will potentially also interfere with the function and the task that the robot collective was meant to solve. And this is one reason why it's super hard to actually generate large collectives of hundreds of thousands of such robots that actually perform a robust and adaptable, collectively intelligent behavior. But how can we improve on that? Actually, we can take inspiration in nature and learn from natural systems how they actually do this, how they use the power of self-organization for exhibiting collective intelligence. And the first way to start is to look, how do actually animals interact in such a collectives? And one way, for example, for fish, what we know is that the social interactions are primarily visual. So they don't talk to each other when they coordinate their behavior, when they exhibit collective intelligence. They actually just watch what their near neighbors are doing and respond accordingly with, for example, certain movement maneuvers. And now we can take the inspiration, and what we did, we actually developed models of artificial agents, first in computer simulation, that only use visual interactions and now try to solve complex tasks, like, for example, exploring and exploiting such a resource environment, so perform collective foraging. And what is great about this algorithm in the computer is we have full control about the behavior of individual agents, so we can truly understand what properties of the agents, what properties of the visual interactions are important for improving the performance of these collectives. Under what conditions do they actually exhibit optimally collective behavior? So this is great. However, these are only computer simulations, and as you learned from all the talks today, hopefully, is we actually want to move into the real world. We actually want to have artificial collectives also performing complex tasks in the real world, and for this we need some hardware. And here we have actually two different species of our robotic agents that we can use to investigate collective intelligence at our cluster. On the left-hand side, we have the kilobots. Very simple robots that on their own cannot do much actually. They can move forward, they can turn left, right, maybe move forward again. They have a sensor that can sense light, and they can communicate in a very limited fashion with their nearest neighbors. But basically, just exchanging some very simple information or messages. So on their own, they are not really intelligent. However, if you put many of such robots together and let them interact, they're actually capable of solving complex tasks which are far beyond the reach what an individual kilobot can solve. On the right-hand side, we have our different species, which are the Timio robots. So they're actually, oops, I apologize for that. They're actually a bit more complex in a sense. The Timio robot itself is this little basis down here, and these are actually educational robots for school children. What we do at SCIoI is we actually complement these robots by a computer on top and a camera, and so in this way we put a brain and an eye on top of our computers, and this way we generate much more capable, cognitively more clever agents that we can now put together and understand how they coordinate and behave in a collectively intelligent way. And with this, we can generate new insights of understanding the principle of collective intelligence. So for example, in this kilobots example, what we can show is that through social interactions, these little robots can accurately estimate the value of the light intensity in this environment, so something like a distributed resource. But even more, they are actually able to capture the light cone by moving around and actually forming a ring around the light cone. And this actually is one example where you can think maybe to inspire new algorithms for something like identifying hazardous substances in the environment and maybe even capturing them, like for example oil spills in the open ocean. On the other hand, for our Timio robots, we actually could show that through minimal vision-based interaction, they're actually able to very seemingly and very adaptively coordinate the movement and explore together our experimental arena at SCIoI. And what is interesting about this purely vision-based interactions is that it would also allow potentially to form groups of robots that cannot communicate with each other, but just can watch each other through visual sensors. And what is also nice is that these action movement patterns look fairly natural compared to other control algorithms for these robots that are proposed in the literature. And if you would just watch the tracks of these robots and you don't know what is actually being tracked, you could actually think, or I actually thought, it looks very much like a fish school that we see in the lab. And this is also something which shows how learning from nature also helps us to improve algorithms for artificial agents. But we can move further. What we, of course, can do, we can actually have full information what the first-person perspective is of such a Timio robot, now here moving and performing some task in our lab space at SCIoI. And this will allow us to really understand what does the different robots perceive when solving complex tasks, when behaving collectively intelligent way, or maybe when actually doing something stupid. And this is something which actually is then something that actually facilitates this loop formation and allows us to develop truly a fundamental understanding of collective intelligence. So on the one hand, the study of vision-based interaction was inspired by natural systems, but of course, in our artificial agents, we have full control about the vision system. We can change its properties, we can change how far they can see, what resolution they have, and now we can see what impact it has on the performance of these systems when solving collective tasks. And this might generate new insights and new ideas for how the diversity of visual system nature evolves, based on the social and non-social environment that the different species live in. And this type of loop that was also mentioned before actually helps us really to understand natural collective intelligence. So for example, for the Mexico system, for what David showed, we actually identified that these fish that perform these Laola waves, these mixing waves, seem to operate in a very special parameter regime, in a very special state between chaos, where there would be permanent diving of the fish, and order, where they basically would stay most of the time at the surface and only very rarely dive. And the fish seem to be really just working or operating at the edge between these two very different states, different regimes. And what is so fascinating about this, that there's actually evidence from neuroscience that the brain might also operate in a special regime between order and chaos. So in a sense, it might help us to understand whether there are some fundamental principles of distributed collective intelligence, whether these are groups of neurons interacting together in neural networks, or actually thousands of brains interacting together in a fish school. Through the study of this predator-prey dynamics that Paulina nicely demonstrated, we have shown how simple heuristics allow the prey to very efficiently evade their predators, but also how simple interaction between predators help them to confine and to control the prey. Furthermore, studying collective foraging, collective exploration, and collective estimation, we actually learned that having sometimes weaker interaction or less interactions might be actually beneficial for the collective. So less is more for collective intelligence. And also we learned that diversity and heterogeneity in the swarming robots is actually beneficial for the performance of these collective systems. And eventually, while we're doing fundamental research, the idea is, or we certainly hope that we can actually contribute how we can use these technologies for the benefits of society. So how, for example, we could use swarms of robots or drones to, for example, perform search and rescue missions following natural disasters. Or how to use this for wildlife conservation, for monitoring of wildlife, for example, to protect it against poachers, or to understand how wildlife adapts to environmental changes, for example, due to climate change. And in the end, you can also think that it might be beneficial to improve artificial autonomous driving vehicles like this one. Because if you think of an autonomous car, it actually has to solve kind of similar tasks as maybe an animal or a fish in a very dense environment. So it wants to avoid collisions, of course. It wants to coordinate with others in its vicinity, while at the same time reaching its final goal. And with this thought, I would like to close, and thank you very much for your attention.